Good morning. Welcome to the today's session of Computer Organization and Architecture. We are discussing the topics of Module 2, and in the previous classes we have discussed about the assembly language and addressing modes, and also we discussed about the basic input-output operation. And now in today's class we will be learning about one more important aspect of any programming, and that is the data structures. So as we all know, data structures are very important in any programming language, and data structures are the building blocks of the programs. Okay, if you consider the complex programs where the data set is very large, in order to handle the data in a very efficient way and not to organize the data, in order to store the data in an efficient manner, okay, it is essential to make use of the data structures. So if you consider the examples of data structures, so we have lists, arrays, stacks, views, etc. as the examples. And we have already seen in one of our example the data structure list. So we have taken an example for the addressing modes. There we had seen the data of a student, and his test marks, student ID and his test marks, which is actually stored as a list of data, an array of data. We have already seen that as example. And now, so we will be discussing another important data structure, that is stacks. Okay, along with the stack we will be considering one more data structure which is very close to the stack, that is weave. Therefore today's topic, what we are going to discuss is stacks and weaves. Yes. Okay, so now let us discuss about stacks first. Later we will consider weave. So stack, as I said, it is one of the data structure. So it is a list of elements which are the words or it may be bytes, so that are organized in a memory. So now if you consider stack, so what is the restriction that we have with respect to stack? So as I said, each and every data structure will be having its own way of arrangement of data, that is storing and management of the data, and stack is restricted by the adding of data and removing of data, that is we can add or remove the data at one end of the stack only. So that is the restriction, data accessing restriction we have with respect to the stack. And if you consider the stack, so its stack will be having top as well as it will be having a bottom. So we will see that when we see the stack in the memory, we will see the stack words in the memory. There we will see so what is meant by the top of the stack and what is meant by the bottom of the stack. And other than these the terms top and bottom that are associated with the stack, we refer this stack by another important term, that is LIFO. So that is last in, first out. Last in, first out. So in short it is called as LIFO. So if you consider stack, we use the phrase last in, first out to refer to the stack. So why? Because so in this, the item which we move to the stack, that is the last item which is moved into the stack, is the first item to be retrieved from the stack. So that we will see when we consider the stack operation, so that you can understand in a better way. Yes. So last in, first out is the phrase which is used. So it is relevant to the accessing, that is how we are going to store the data and how it is retrieved. So the last item which is being moved into the stack is the first item to be retrieved. Therefore we call this as last in, first out. And there are other two terms which are used in relation to the stack, and those are push and pop. And this is placing of a new item into the stack, and this is removal of an item from the stack. So in order to place the data, in order to move the data, new item, new data into the stack, we use the term push, whereas in order to retrieve the data from the stack, we use the term pop, okay, and these are the terms, okay, that are associated with the stack. Now let us consider, okay, the stack words in the memory. Let me call this as 0th address. Yes. Let us assume the stacks run through this, okay, and let me assume this is the last, okay, address location in the memory. Yes. So let me, so this is SP. I'll tell you what is SP later. Yes. So this is the current top element, and this is the bottom of the stack, and this is the stack, okay, segment in the memory. And here let us assume the data which is present is minus, okay, 28, 43, etc., some 279. We have, okay, these data elements in the stack. Yes. So this represents the stack words, okay, or you can call bytes in the memory. And if you observe, I have written SP here. So this is called as stack pointer. So a pointer, a register is required in order to hold the address of the, that is the top address of the stack. So in order to hold that address, we use a pointer called as stack pointer. So that will be having an address which is always the top of the stack. Okay, so the top element, the current top element of the stack, okay, so that address is contained by the stack pointer. And if you observe, I have written the bottom, so this is the value we have is 279. So here whenever we add the data, the data will be added, okay, so that the SP will be incremented and the new data item will be added. Whereas for retrieving the data, so we have to decrement this, that is we have to copy this and then we have to decrement the stack pointer. So now after seeing this, so let us, okay, consider the instructions that we use in order to push and pop the data. So before that, so what are the other things we need to understand about this is, so the stack grows in the reverse direction. That is, if I assume the stack, okay, is starting at location, let me, okay, write it as stack itself. So stack is starting at location 2000, then so the first element will be placed, okay, in this, and it will grow along the decreasing addresses of the memory. So if I want to define the stack segment, okay, say I want to allocate 500 bytes of data, then so I'll be assigning the memory segment, okay, from 1500 to 2000, okay, as the stack segment, and in this the elements has to be stored. So if you want to store the element, the stack pointer will be pointing, okay, the 2004. So why? Because is, so before adding the data into the stack will be decremented by 4. Because of that reason, so we are saying that the stack pointer initially contains 2004 as its value, and the first element, okay, will be placed in 2000 by decrementing this by 4 if it is a 32-bit computer. So we have already assumed that in our discussion we will be considering the standard word length as 32-bit. So I am saying the stack pointer will be decremented by 4. So it will be decrementing and it will be placing the first element in 2000. Therefore, so the stack grows in the reverse order, okay, so it grows along the lower address of the memory. Yes, so this is about the stack, okay, and the stack words in the memory. Now as I said, so in order to perform the operations like push and pop, that is in order to add the data into the stack and in order to retrieve the data from the stack, so let us see what are all the instructions we have. Yes, so if you consider the instructions, so as I just now, okay, mentioned that the stack pointer, okay, is the register, so which is used to store the current address of the stack. Initially, as I said, if I want to store, okay, the element, first element in 2000, where 2000 is the the last address of the stack segment, and 1500 is the first address of the stack segment, and the stack pointer will be initially loaded with 2004 so that it points to 2000 after decrementing. Therefore, so if you consider the instructions, so we will be having the instruction for push operation as subtract 4 from the stack pointer, then move new item into the contents of stack pointer. Yes, so these are the instructions we use in order to store a new element into the stack. Okay, then if you consider the pop operation, then the instruction move contents of SP into item, add to SP, because so when we copy, it is going to be point to the next address location. So this, for example, the current content of SP is -28. If -28 is moved into the item, the location item, then this will be pointing to the next top of the stack, and next top of the stack will be 17. Therefore, so we have to add 4, because if you observe, so here let us assume we have some 16 as the location, and this will be 20 after the pop operation. Therefore, it has to point to the next location, next top of the stack. Because of that reason, we need to add 4 to the stack pointer if it is a 32-bit computer. So these two are the code segments which are required in order to perform push and pop operations. And now let us see the effect of this push and pop operation on the stack. So how the elements so will be changed according to these operations. So if you want to consider, yes, let me consider this itself, and let me write yes, so let me consider another similar segment, because we need to illustrate two operations. So now let me consider 0th location, this is the 0th location. Next we have -28, 17, 43, etc. So the end of the stack, so let me assume the same, that is 279. Yes, so let me assume this is the last location in the memory, that is 2 power k minus 1. And let us assume this is illustrating the push operation, and this is used to illustrate the pop operation. Yes, so now if you consider the first one, so see that we have used new item. So we have some data in the new item location. So let us consider new item as the register, or some memory location, and in this case let us consider item as the memory location. Now let us see, so what happens in the first case. See, so subtract 4 from the stack pointer, subtract 4 from the stack pointer as we assumed. Let us consider this as 16, this as 20, this is 24, etc. Let this be some location, and depending on the number of elements in the stack, so this will be having certain address location. So for time being, just let us consider we have 16, 20, 24 as the initial addresses. Yes, so now when we want to move the item, new item, as I considered before, let this be 20. So now decrement or subtract the stack pointer by 4, and place the data new item into the contents of the stack pointer. If you decrement this, so that will be pointing to the previous location, that is 12, and the contents of this will be copied into contents of the stack pointer. Therefore, for the memory location, you will be copying the data, that is 20, into the memory location 12. So this is the push operation. Whereas if you consider the pop operation, so we have to retrieve the data. Therefore, in the pop operation, see, so move the contents of, initially let us assume the stack pointer is here. In this case also, initially the stack pointer is here. Stack pointer is pointing to the top element of the stack. So we have minus 28 as the element. So we have to copy that minus 28 into this memory location, and then so we have to point to the next top of the stack. So if this is the top of the stack, next stop is this one. So we have to, here we have an address of 16. So in order to point to the next top of the stack, plus 4 must be added so that it goes to the next top of the stack, that is 20. Okay. So this is how the push and pop operations are going to affect the contents of the stack. Okay. And now if you consider the instructions what we have, okay, so we can write or we can replace these two, okay, segments by single instructions. That is, these two can be replaced by a single instruction and these two instructions can be replaced by a single instruction. So if you consider the first one, so we are subtracting, okay, and then we are moving. So instead of writing like that, you can write a statement move new item minus SP, and for the second, okay, code segment you can replace that by move yes. So I have already mentioned in additional addressing mode that we will be using the auto increment and auto decrement in conjunction with the stacks. So here you can observe we have used auto increment and auto decrement. So here we have auto decrement. So this is the reason why we have the operation of this auto decrement as first decrement, then copy the content. Okay. So that is the operation which is required in case of a stack. Okay. Yes. So this is about the instructions that are involved. Now if you consider the stack, so as I said before, if you assume the stack runs through 1500 to 2000, okay, if you use such an instruction, then it is not possible to keep track of what is the starting address of the stack and what is the ending address of the stack. That is, you cannot keep track of the first element and the last element in the stack. So this may result in the error, that is when we try to push or when we try to retrieve the data, it may result in some junk data, because so if the pointer, stack pointer is pointing to 2004 and if you want to copy that data, then so that will copy the data which is so out of the stack, therefore so that is not the required data to be copied. Similarly, if you want to push the item, okay, if it is beyond this, then it will not be pushed into the stack for the later uses. Therefore, in order to avoid full and empty conditions of a stack, okay, so we will have to replace those single statements by code segment which is consisting of more than one instructions. So next we will see so how to avoid the stack full and stack empty conditions so that we avoid the retrieval of the wrong data from the stack. Yes. So now let us see how to avoid the full and empty conditions, okay, in case of a stack. So in order to see that, we will be using an instruction compare, okay, in order to write the code segment for avoiding the errors. Yes, so if you consider this, we have compare the general format, compare source comma destination. So how this is going to work is, this is going to subtract the source from the destination and the subtraction result will be moved into destination. So now we will be using this, okay, while writing the code segment for the error-free push and pop operations. So now let me consider the code segment. Let me call this as safe pop, okay, next as safe push. Yes, so now compare hash 2000 with stack pointer. Okay, compare hash 2000 with the stack pointer. So now let us see what has to happen depending on the result. So if the result is greater than 0, if you are getting the value which is greater than 0, then it has to jump to pop error. Otherwise, it has to move SP plus comma item. So if you observe, so what the first instruction says, so compare hash 2000 with the stack pointer. So if I assume the stack pointer, okay, is pointing to a location which is beyond this. If I assume the stack pointer is pointing to the location which is beyond this, let me assume it is 2004 initially. Okay, we load the stack pointer with 2004, that is different. So this is while push and pop operation I am speaking. So if it is pointing to 2004, okay, and the subtraction result, so 2004 minus 2000 will be 4, which is greater than 0, so that indicates that it is out of the stack. So stack pointer is pointing to an element which is out of the stack, so therefore it has to go to routine, so that is given by pop error. Okay, otherwise, so if it is above this, so say some, okay, previous location, just let us assume, so we have the stack pointer at this location. So if that is the location, then so it has to copy the contents of the SP into the item. So that is, so the pop operation has to happen if the compare result, okay, is less than or equal to 0. Yes. Next, let us consider the safe push. Let us see, so what are all the instructions that must be written so that we can have a safe push operation. So we have to compare with 1500, okay, because we cannot push the data beyond this because the stack is ending at this point. So 1500 with the stack pointer, and here the condition or the result to be checked is the opposite to that, that is it should be less than or equal to 0. So if that is the case, then we should go to push error, and the instruction, so if this is, okay, if the comparison result is not less than or equal to 0, then it has to move, that is it has to go to the next instruction, that is move new item into the stack. So in order to understand this, let me consider, so we have so now let us consider how this safe push, okay, if you write this instruction, how this will be executed. So in order to understand this, so let me consider, okay, the current address of the stack pointer as this 1496. So if you assume this is the current location, then that subtraction result, when we subtract 1496, okay, that is when we subtract 1500 from 1496, then it is going to give you a negative result. So in that case, it is going to execute the push error. So push error will be executed. So then in case if you have the stack pointer, okay, address as 1504, in that case, so the subtraction result will be a positive one, it will be greater than 0, therefore so error will not occur, this will not be executed. It is going to execute the next instruction, that is move new item comma minus SP, that is it's going to decrement later, it is going to copy the content of new item into the stack pointer. Okay, this is about the stack and the instructions which are used to safely perform the push and pop operations. Now let us consider the queue and let us understand what is the difference between a stack and queue. So queue is also a data structure, okay, and so it is very similar to the stack, but in that case, that is in the queue, we will be having the data accessing in the form of a first in first out format. So in case of stack, if you consider, it was last in first out, and queue is first in first out. So if you consider the queue, so it will be in this form. This is back end and this is front end, okay, and N queue, so D queue. Similar to the push and pop operation, we have N queue and D queue, okay, as the operations related to the data structure queue. And if you consider the stack, okay, so here the direction of the data elements, that is accessing of data elements, if you observe, see here in the queue, okay, giving the data from one side and retrieving the data from the other side. So if you observe, the first element what we are going to place on the queue will be this one, and the first element, okay, which will be removed is also this one. Therefore, so this we call as FIFO, whereas, okay, stack, if you observe the direction of the data elements, okay, movement of data elements, you can see, so it is pushed from here and popped from here. Therefore, so the last element which is pushed will be the first element to be popped. Therefore, this is referred as last in first out. So this is the difference between the stack and the, okay, queue. And if you consider in the previous discussion, we have a register called as stack pointer in order to hold the current address of the top element. So we required only one, okay, register in case of the stack. But if you consider the queue, okay, it is a different condition. We may require two pointers, okay, one to point to the front end of the queue and other to point to the back end of the queue. Yes, so now if you consider queue, so it is essential to keep track of both the ends. So, and if you observe, both the ends grow in the increasing order of the memory locations. So if you consider, so see here, we are going to dequeue. So when we dequeue, okay, it is going to grow in the increasing order. Similarly, NQ is also growing in the increasing order. So if you want to understand in a better way, so I can, okay, so give some memory location, memory addresses to this. So if this is 1500, okay, then this will be 1504, etc. This is 2000. So in this way it is going to grow. When we, okay, dequeue, it is going to point to the next location which is at higher address compared to the, okay, previous address. Similarly, when we enqueue, so it is going to place the new item to the address which is, okay, greater than the previous address. Therefore, both are going to, okay, both are growing towards the increasing value of the addresses. And if you consider queue, if you do not have any control, okay, if you do not control, then it may grow throughout the memory. So in order to avoid, you can use a buffer, okay, you can use a circular buffer in case of queue in order to avoid such conditions, okay. If we consider queue, let us understand how this circular buffer is going to, okay, control the growth of the queue. So let us consider the queue is starting at beginning, and let us assume end is the memory location, so where the queue is going to end. If you consider the beginning and end of the queue, yes, so let us assume the initial or the first element, okay, is placed in the memory location beginning, and when you keep on placing the successive data elements on the queue, so it will be moved up to the end. So if you are using a circular buffer, in that case what we are supposed to do is, when it reaches the point end, that is when it reaches the memory location end, so we have to, okay, reset the value of the pointer, that is the circular buffer pointer, so to the address of the beginning. So we are going to, okay, reset the address and we are going to start from the beginning. By the time the queue reaches its end value, beginning, okay, we will be having some free space because of the retrieval operations. So if you have copied some data, so there will be free space at the beginning. Therefore, so before reaching, okay, once it reaches the end value, it is going to be reset and it will be starting its operation once again from the beginning point. Therefore, so this is how, okay, we are going to control the growth of queue in a memory by using a pointer, okay, by using a circular buffer you can achieve this controlling action. So this is about the data structures, queue and the stacks, okay. And next we will be discussing about another important aspect in a programming, that is the subroutines. So why we have discussed this stacks is usually we will be using stacks, okay, in conjunction with the subroutine, because the stack is going to give the control and the information linkage between the subroutine and the main program. Sometimes it is essential for us to write a program, okay, so wherein we will be having an operation which is to be performed n number of times, or we will be having a program segment which is to be repeated n number of times. In such cases we will be placing that, okay, set of instruction in a routine called as subroutine, okay, and in the next class we will be discussing about the subroutine. Thank you.